Hello everyone, welcome to lecture 5 of linear algebra. In this lecture, we're going to discuss eigenvectors and eigenvalues. So first, the definition of eigenvector and eigenvalue. So an eigenvector of an n by n matrix A is a non-zero vector x such that ax equals to lambda x, and the corresponding lambda, the scalar lambda, is the corresponding eigenvalue. Um, and it is easy to determine if a given vector is an eigenvector of a matrix. So let us do an exercise. So if our A is 1, 6, 5, 2, and U is a vector 6 minus 5, with our V being the vector with 3 and minus 2. So we're going to determine if U and V are eigenvectors of A. So firstly, by our definition, if we going to check U first, so that is AU equals to lambda U for some lambda in real. So that means 1652 times our U, 6 minus 5, and this guy equals to, so 1 times 6 minus 6 times 5, which is minus 24. And the remaining is 5 times 6 and minus 2 times 5. So that gives us 20. And this guy equals to, if we plug out a minus 4, we have inside 6 and minus 5. So that is minus 4 of U. So that satisfies the definition of being an eigenvector. So U is an eigenvector of A. And now let us check V. So we do the same for V. And we have 3 minus 12, which is minus 9. And on the second row, we have 11. However, we can see that there exists no such an lambda, such that lambda minus 9, 11 equals to our U. So lambda U equals to this guy. So this is V. So V is not an eigenvector of A, since since AV is not a multiple of V. And let us do another exercise. So now we are given an eigenvalue 7. So we see that 7 is an eigenvalue of matrix A, where A is defined same as above. And we want to find the corresponding eigenvector. And our solution is that since the scalar 7 is an eigenvalue of A, so that means AX equals to 7x. And that is equivalent to, say, a minus 7, of course, 7 times the identity matrix, 2 by 2 identity matrix equals to, and then times x equals to 0. So to solve this homogeneous equation, and we know that our x is defined to be non-zero. So That means we need to have non-trivial solution for this equation, this homogeneous equation. So let us compute this, guys. So we have a minus 7 times 1, 0, 0, 1. So that is 1 minus 7 and 6. And here we have 5 and 2 minus 7. So that gives us a minus 6, 6, 5, and a minus 5. And the columns of this matrix, this A minus 7, I2, are obviously linearly dependent. Therefore, it has non-trivial solutions. So we now have proved the existence. It remains to find the exact eigenvector. So um, to find that the corresponding eigenvector, we need to use the row operation. So that is minus 6, 6, 5, minus 5, and the augmented matrix 0, 0. And it is row equivalent to 1, minus 1, 0, 0, 0, 0. So the general solution has the form x2 times 1, 1, since we have x1 equals to minus x2. And each vector of this form with x2 not vanishing is a vector corresponding to lambda equals to 7. So this is the general solution. And it is important to note that although we used the row reduction to find the eigenvectors, it cannot be used to find the eigenvalues, since our row operations may change the eigenvalues. So an echelon form of a matrix A usually does not display on eigenvalues of A, usually does not display the eigenvalues of A. And note that in solving this equation, we have an equivalence statement. That is, 8x equals to 7x if and only if A minus 7 times the 2 by 2 identity matrix together then times x vanishing. So this equivalence relation holds for lambda, not only when lambda is the eigenvalue. So we can say that the lambda is an eigenvalue of an n by n matrix if and only if so lambda is an eigenvalue of an n by n matrix A if and only if our A minus lambda in times x equals 0 has non-trivial solution. And the set of all these solutions is just the null space of the matrix A minus lambda in. So since we know that null space is a subspace of Rn, so the solution of all the non-trivial solution is still a subspace of Rn, and we call this the solution site. So for all x such that x lives in Rn, and a minus lambda in times x vanishing. So this site is called the eigenspace. Of course, the eigenspace of matrix A, and it is corresponding to the eigenvalue lambda. And the eigenspace obviously consists of the zero vectors and all the eigenvectors corresponding to lambda. So it is important once we know a subspace that the corresponding basis for it. So let us do an exercise. So if our A equals to 4, minus 1, and 6, 2, 1, 6, and 2, minus 1, 8. And we know that one of the eigenvalue of A is 2. And now we want to find a basis for its eigenspace. So to find the eigenspace, it is equivalent to find all these non-trivial solution of a minus 2i3 vanishing. So this equals to 4 minus 2 minus 1, 6, and 2, 1 minus 2, 6, 2 minus 1, and 8 minus 2. And this gives us a 2 minus 1, 6, 2 minus 1, 6, and 2 minus 1, 6. And now we shall use row reduction on the augmented matrix for this guy being 0. So that is 2 minus 1, 6, 0, 2 minus 1, 6, 0, 2 minus 1, 6, 0. This row equivalent with only the first row being non-empty. And at this point, it is obviously that 2 is indeed an eigenvalue of A, since our A minus 2 lambda 3 times x equals to 0 has free variables. So we have in the first row that 2x1 minus x2 plus 6x3 equals to 0. So we have that x1 equals to 1 half x2 and then minus 3x3. So the general solution for our a minus 2 I3 x equals to 0 is equivalent to x2 times 1 half 1 0 and then plus x3 minus 3 0 and 1. So this means that we have x1, x2, and x3 where we have 1 half x2 plus minus 3x3, and it is x2 and x3, where we know that this equation equals to x1. So we know that x2 and x3 are free variables. So the eigenspace is a two-dimensional subspace of R3, and the basis for this eigenspace is given by 1 half 1 0 and minus 3 0 and 1. So this gives us the first result of this lecture, that is the eigenvalue of a triangular matrix. Eigenvalues are the entries of the main diagonal. So what does it mean for a matrix to have an eigenvalue of 0? So if we have ax equals to 0x by the definition of eigenvalue, so for this guy to have non-trivial solution, we have 0 being an eigenvalue if and only if this equation has non-trivial solution. So this means our ax has to vanish, and it has non-trivial solution if and only if a is not invertible. So that is, a has determinant being 0. So we know that an equivalent statement for our matrix for having 0 as an eigenvalue is that a is not invertible. So we have lambda a sun, 0 is an eigenvalue of a if and only if a has determinant 0. And we have another theorem. So if V1 up to Vr are eigenvectors corresponding to distinct lambda 1 up to lambda r eigenvalues of an n by n matrix A, then we have this site V1 up to Vr is linearly independent. So now we shall go to the next topic of this lecture, the characteristic equation. So useful information about the eigenvalues of a square matrix A is encoded into a special scalar equation, which is called the characteristic equation. So let us use an exercise to find out why. So if we are going to find the eigenvalues of the matrix A equals to 2, 3, 3 minus 6. So we first need to find all scalars lambda such that our A minus lambda I2x has equals to 0 has non-trivial solution. So according to the invertible matrix theorem, this problem is equivalent to state that our matrix A minus lambda I2, it has determinant being 0, so that means it is not invertible. So we have that the A minus lambda I2 equals to 2 minus lambda and 3, and 3 minus 6 minus lambda. So this is the matrix, and we're going to calculate its determinant. So the determinant of this guy equals to 2 minus lambda and times minus 6 minus lambda, and then minus 9 equals to 0. So that is, we have minus 21 plus 4 lambda plus lambda squared. So that is lambda minus 7, plus 7 and lambda minus 3. So we have that when lambda equals to minus 7 and lambda equals to 3, we have this equation being satisfied. So these two values are the desired eigenvalues. So we have a modified inverted matrix theorem. So let A be an n by n matrix. Then the followings, then the belows are equivalent. So still our first statement is that A is invertible if and only if 0 is not an eigenvalue of A, if and only if we have it has determined non-zero. So in fact, only the second statement is new here. And we see that a scalar is an eigenvalue of an n by n matrix if and only if lambda satisfies the so-called characteristic equation, namely the determinant of A minus lambda I n equals to 0. So we shall define the so-called characteristic polynomial if A is an n by n matrix, then the determinant of A minus lambda I n is a polynomial of degree up to n. So in this case, we just say it has degree n, called the characteristic polynomial for A. So in general, we know that for the factorized polynomials with the form, for example, x minus 3 squared times x plus 4. So we know that it has three solutions since the order is 3, degree is 3. So, but we know that there are 3 and minus 4. But since for the first part it has a power of 2, so that means the algebraic multiplicity of 3 is 2. So let us use an example to have a better understanding for it. So if the characteristic polynomial of a 6 by 6 matrix, namely lambda 6 minus 4 lambda 5 minus 12 lambda 4, and we want to find all its eigenvalues and their multiplicities. So if we plug out the common factor lambda 4, we have lambda squared minus 4 lambda minus 12. So it is equal to lambda 4 times lambda minus 6 and then lambda plus 2. So we have that the eigenvalues are that lambda equals to 0 with multiplicity 4, and the lambda equals to 6 with multiplicity 1, and the lambda equals to minus 4 with multiplicity 1. And since the characteristic equation for an n by n matrix involves an nth degree polynomial, so the equation has exactly n rows counting multiplicities. providing the complex roots are also allowed. And the complex roots are called complex eigenvalues. So now we state a theorem that illustrates one use of the characteristic polynomial, which provides the foundation of several iterative methods in approximate eigenvalues. So this is very important in statistics and probability, and in most applications, this is called the similar matrix. So if A and B are n by n matrices, then we say that A is similar to B if there exists an invertible n by n matrix, or not necessarily. So let us just not to state its dimension, just to make sure it's the general in the general form. So there exists an invertible matrix P such that we have P inverse A P equals to B, or equivalently we have A equals to P B P inverse. So now we can prove that this similar relation, since this is a binary relation, and it looks pretty like the equivalence relation. So let us prove that it is indeed the equivalence relation. So in saying the equivalence relation, we need to first check the reflexive, and we also need to check the symmetric, and lastly the transitive. So for reflexive, we have that P inverse A P equals to P A P inverse. So if we left multiply P, since it is okay, so let us write I on the right hand side. So write A. So since P is invertible, so we left multiply by P, and right multiply by P inverse. So we have A equals P A P inverse. So the reflexive, the first condition is satisfied, and also the symmetric. So so the symmetric is that if A, so A equivalent to B, we have B equivalent to A. So that is P inverse A P equals to B, and we have A equals to P B P inverse. So this relation holds automatically by our definition. And also for the transitivity, one can prove themselves that for A equivalent to B and B equivalent to C, we can have that B equivalent to, A is equivalent to C as well. So yes, this relation is the equivalence relation. So that is why this is so important in practice, since we can use for example, okay, we need more terminology to state why it is so important. Before that, we note that changing A to P inverse AP is called a similarity transformation. So now let us prove a theorem which states that if n by n matrices A and B are similar, then they have the same characteristic polynomial. So they have the same characteristic polynomials, and hence the same eigenvalues, of course with the same multiplicity. Made a typo. Multiplicity. Okay, so let us prove it. So if B equals P inverse AP, for P is an invertible n by n matrix, then we have B minus lambda in equals to P inverse AP minus lambda P inverse P. Since P inverse times P is an n by n identity matrix, so it is equivalent to this guy. So we have B minus lambda in equals to we first plug out P the left so we just interchange the order. So we have P inverse times so we have P inverse times lambda times P, and we have a left multiplied by P inverse, and then the inner inside we have A minus lambda in, and we have a left multiplied by P. So that is our determinant of B minus lambda in equals to the determinant of this whole thing, P inverse A minus lambda in times P. And since P inverse and A minus lambda in and P are all n by n matrices, so we know that the determinant of their product equals to the product of their determinants. So we have this guy. And moreover, since these are only since this is the multiplication of numbers and we can apply the associativity, so we have that determinant of P inverse times determinant of P, then times the determinant of A minus lambda in, and still we know that the multiplication of the determinant equals to the determinant of the multiplication. So that is in fact the in. And we know that it is only one, so let us cancel this guy. So we have the desired A minus lambda in. So the equation is constructed and we are done. Remark. So first, note that in this theorem, we know that if A is equivalent to B, then they have the same characteristic polynomials, hence the same eigenvalues with the same multiplicity. But if they have the same characteristic polynomials and the same eigenvalues with the same multiplicity, does not necessarily to mean that A is equivalent to B. So yes, the converse of Theorem 4 does not hold in general. So let me offer an counterexample. So consider the matrices 2, 1, 0, 2, and 2, 0, 0, 2. So they are not similar, but they have the same eigenvalues. One can check it as an exercise. The second remark is that similarity is not the same as row equivalence. So similarity is not the same as row equivalence. In fact, it is stronger than row equivalence, which means if A is rho equivalent to B, we know that B equals to EA, where E is an invertible matrix. And moreover, the row operations on a matrix usually change its eigenvalues. We have noted that in the previous remark, somewhere above. And yeah, so this theorem states implies or offers some insights for why the the similarity is so important, since for some not well-behaved matrix, we can use this similarity property to approach it uh, by some members in its equivalence class, so that we can perform or we can approach A uh, with less error as possible. Okay, so this summarizes the materials of this lecture, and in the next lecture, we have mentioned a bit about the complex eigenvalues. So in the next lecture, we're going to talk about the complex eigenvalues, the diagonalization, so which is an extension for this guy, where our P is um, uh, P is an invertible matrix and an inner one instead of A or B. It is a diagonal matrix which possesses more powerful properties. Um, and also we will talk some about the eigenvectors and linear transformations in the next lecture. Um, and then we shall move to the next topic. Okay, so thank you for watching, and see you in the next lecture.